Already. Good afternoon, class. Here's chapter 3, derivatives, and the last section, 3.8 differentials and linear approximation. We've already done various differentiation formulas. Now we're going to look at differentials and linear approximation, which in essence is an application of that. On this page, of course, you see differentiation formula starting with the definition, basics, product rule, quotient rule, chain rule, exponential rules, logarithmic and rules. So we got them all here, and I want to remind you of a log and what it means. If you look at this one and pay attention to the concept that this arrow gives you, now we can write it as b to the power of y equals x, meaning if I can go from one format to the next, and vice versa, I'm comfortable with the concept. And therefore, the properties that we see here for the general case with base b, by the way, the base must be positive, can't be 1. So log of 1 with any base is 0. Log of base b, of base b is 1, because when the argument and log are the same, the answer is 1. These two refer to the fact that exponential functions and logarithmic functions are inverse of each other. And this is the product rule, quotient rule, power rule. We can go to common log, in which case the base is 10, and we write log without the base. That means common log. So we can see the properties of logs in that case. When we write ln instead of log, that means the base is e. We can see those properties. And if we graph y equals e to the power of x, y equals ln x, they are inverse functions. Therefore, they are symmetric with respect to the line y equals x. This is the change of base formula. The derivative of a log, basically ln x, you flip it over, ln of g of x, you flip it over times g prime by the chain rule. And to find the log when the base is no longer e, we use the change of base formula. And we divide by ln b. If you recall, in the case of exponential functions, if the base is not e, we multiply by ln b. In the case of a log, based on change of base formula, we divide by ln b. And that's the difference between the two, and that's because they are inverse of each other. So the reverse process. 3.8 differentials and linear approximation. Here's a definition for y equals f of x. Some care y equals f of x. We define dx called the differential of x by dx equals delta x. As we go from P to Q along the x-axis, we cover a distance. This distance from D to C or from P to B is equal to delta x or dx. That's what we call it. So the distance along the x-axis is dx or delta x. And dy, called the differential of y, we define it by dy equals f prime of x dx. First, I want to show you and remind you that f prime of x is dy dx. The cross product will give us dy f prime of x times dx. That's how you calculate it, okay? As far as the graph is concerned, I want to make sure we understand what we are dealing with here. Okay, so as we go from P to Q, we discussed delta x or dx are the same. But what about the change in y? Okay, so the change in y is C along the curve is CQ minus dp or just BQ or delta y. So delta y is CQ minus dp, which gives rise to delta y, change in y along the curve, equals this distance of BQ, and it's f of x plus delta x. F of x plus delta x is this distance, right? CQ. And f of x is this distance, dp. So f of x plus delta x minus f of x is delta y precisely. We can replace delta y by dy for a function f, which is a continuous function and differentiable function with a small delta x if delta y is difficult to evaluate. So what we are saying is that we know f prime is dy dx precisely. Roughly, it will be delta y over delta x. And therefore, instead of saying that dy is f prime of x dx, we're going to say delta y is equal to that. And by the way, whether I use dx or delta x makes no difference. And so delta y can be approximated by this. This is the precise value. It's an approximation. So the question is, what is the dy as far as the graph is concerned? So this is the curve, and at point P, when we draw a tangent line, again, this distance is along the x-axis, it's delta x dx, they're identical. Now the distance along the y-axis for the tangent is called dy. So this distance AB is dy. So what we are saying, dy, this distance is different than delta y, which is distance. They are not the same. But we can approximate delta y by dy as long as this distance of delta x or dx is small. The smaller the delta x or dx, the better this approximation. Now take a look. So delta y is f of x plus delta x minus f of x. So if I want f of x plus delta x, I can move minus f of x to the other side, becomes plus f of x. So f of x plus delta x is f of x plus delta y, precisely. We said f prime of x is dy dx, and therefore dy is f prime of x dx. So over here, this equation, we keep f of x. We can change the delta y to dy because it's normally easier to calculate, and that's an approximation. Also, so this point has coordinates a and f of a. Also, we want to discuss the linearization. And all I want you to remember, linearization is just the tangent lines. So anyone that says find the linearization of a function at a point, they give you a point, a comma f of a. Or they may give you the x coordinate, you plug it into the y, you get both coordinates. Just use the good old point slope from elementary algebra. Notice if I move the y1 to the right side, I get the second equation. If I change the m to f prime of a, and this pair a comma f of a, so x minus x of 1 is x minus a, and y1 is f of a, I get to this formula, and now I'm going to call it L of x. Do I have to memorize that? No, just remember the point slope. It's very simple, everybody. Let's look at some examples. F of x is given as 4x cubed minus 3x. We want to find dy and delta y with those values. So first, dy, the moment you hear dy, find f prime of x, differentiate. 12x squared minus 3. And then dy is simply the product of this and dx. So what you do, just tag along dx. That's all you have to do. And that's dy, everybody. Just tag along dx. Evaluation is elementary algebra. Plug in 3 instead of x. Dx is 0.2. When we do that, of course, this can be done by hand. This is 9 times 12 is 108. Minus 3 is 105. 105 times 2 is 210. You have one decimal, becomes 21. 1 0 cancels out one decimal. If you want to find delta y, then we are going to use the formula for delta y, f of x plus delta x minus f of x, which means f of 3.2 minus f of 3. So we have to go back to the original function, replace the x with 3.2, replace the x with 3, and look at their difference. That's what we are interested in. F of 3.2 minus f of 3, you plug in 3.2, you plug in 3, and you evaluate using, you can do it by hand, or you can do it with a calculator, especially for this one. So this is not a big deal, it can be done by hand, but calculate, and the first brackets give us 121.472. The second one gives us 99. Subtract from it, we get 22.472. Notice dy has a value of 21. Delta y has a value of 22.472. They are not the same, but they're fairly close. Now, what makes it even closer? The smaller the value of delta x in compared to x, the better the approximation. So if I change this to 0.1, the two numbers become even closer. If I change it to 0.01, if you change this to 0.01, notice this is much smaller than 3, and I highly recommend you try it at home. If you evaluate it, you see that the two are almost identical. That's how close they become. All right, we want to do applications. Anybody wants to read this question for us? Anybody? The radius of a blood vessel is 1.4 millimeters. A drug causes the radius to change to 1.3 millimeters. Use differentials to find the approximate change in the area of a cross-section of the vessel. So first and foremost, recognize the cross-section is a circular shape, which means we are discussing the area. We must know that the area is pi r squared. So whatever the radius is, the drug causes it to change. In fact, it's going to get smaller. So here's the original one, whatever it might be. This case, of course, is 1.4. Here's the new one because it's got smaller. And the difference between these two, is your dr or delta r. So what is given? R is always the original one. So R is 1.4. dr is the difference between the two. the new one minus the old one. The new one minus the old one, meaning a negative value, everybody. So 1.3 minus 1.4, negative 0.1 millimeters. And of course, A is pi r squared. We want dA because we want to use differentials to find the approximate change. Even if they don't say the differentials, that's what they mean here. So we are going to differentiate that, and we remind everybody that f prime is dy dx. So a prime is dA dr because a is a function of r. Therefore, dA, so remember, dy is the product of these two, f prime of x dx. So dA is the product of these two, a prime of r dr. So let's find this by differentiating pi r squared. We get pi times 2r. Okay, maybe I write that. So if I want to differentiate a pi times r squared gives me 2r, so I have 2 pi r. Therefore, dA is this times dr. And now it's time to plug in. Now it's time to plug in. We keep the pi as an exact answer. The r is 1.4. That's why the given is extremely important when you write it. So this becomes 1.4. The r is negative 0.1. And as far as the units of dA is the same as the units of A. And you can see that because this is the radius in millimeters. And so is this one in millimeters. And so when you multiply 2 times 1.4, you get 2.8 times 0.1, you get 0.28. So we have minus 0.28 pi millimeters squared. This is an exact answer. And you really need to practice with that as a calculus student. This is your exact answer. Now, if you replace the pi using a calculator and with a bunch of decimals, you get negative 0.8796 millimeters squared. Please understand, they asked us to approximate the change. We can actually come up with the exact answer, which is delta A. Remember, this was the exact answer, delta Y. So what would be the exact answer? What would be the exact change? Anybody? What do you think we can find the exact change instead of an approximation of the change in area? Can we find the exact change in the area? Well, all we have to do calculate the area of the two circles. One of them with the 1.3 radius, one of them with the 1.4 radius. The difference is the answer. That's why this is pi r squared. I've factored out the pi. So negative 0.27 pi. If you compare these two, they are extremely close. And class, this is the exact change. The area of the smaller one minus the area of the larger one gives you the exact answer. A bacterial colony has a population of P of t equals 20 t over 10 plus t squared in millions t hours after the nutrient is introduced. Use differentials to approximate the change from t equals 2 to t equals 2.4. So t is 2, dt, the change in t is 2.4 minus 2 or 0.4 dt or delta t, that's the given. And here's P of t, since we want to use differentials to approximate the change. That means if a P of t is given, a P prime or dp dt. Therefore, we want dp, which is the product of these two. So that's what we are looking for, everybody. That's what we are looking for. Well, to find p prime of t or dp dt, we need to differentiate this using the quotient rule, f over g. So I'm going to write that as f prime g minus g prime f over g squared. So I'm going to write 20 times 10 plus t squared minus g prime 2t times the top 20t. And I write the bottom just the way it is. I don't change it. I put it in a parenthesis and square it. So that's the quotient rule, everybody. That is the quotient rule. The rest is pretty straightforward. Uh, we are going to simplify the numerator. This is 200 plus 20t squared minus 40t squared. These two combine to negative 20t squared. And dp is the same thing times dt. Replace the t with 2 and dt with 0.4, everybody. So replace the dt with 0.4. So plug in. So this is 4 times 20 is 80. So 200 minus 80. And this is 4. So we have 14 squared. 120 divided by 14 squared times 0.4 gives us 0.245 millions. So it's important to see where this number comes from. That is extremely important to see that. Now, of course, that means $245,000. Can we find delta P instead of dP, instead of approximation? Can we come up with the exact answer? The answer is yes. Find delta P. So what is delta P? Plug in 2.4 into P of t, plug in 2 into P of t, and their difference. So when you do that, when you go through the process, you get 0.189, which means, now let me use a different color, 189,000. Now, one might say, well, there's a huge difference between the two. Please understand, 0.4 compared to t is pretty large. If it's small, again, the smaller this value of dt or delta t, compared to the t, the better the approximation. And that's really the key. So again, this number is pretty large compared to t. But if you change it to 0.1 or 0.01, then it becomes excellent, almost identical. Use differentials to approximate 51 squared. Well, when you want to do that, first you have to see what type of a function it can be representing. You are squaring 51. That is the action you're taking. So you let f of x be x squared. If you're raising it to the power of 5, then you let f of x be x to the power of 5. If you're taking a root, square root of 51, then you let f of x be square root of x. The next step is choose a number, x, close to 51, for which squaring is easy to compute. You can do it in your head. And I hope everybody can see that the closest number we can think of is 50, and everybody should know 50 squared is 2500 because 5 squared is 25 and 0, you're gonna have 2 of it. Okay. And now, what is delta x or dx? We are going to work with 50 to get to 51. So 51 minus 50 is 1. In other words, it gets larger. So this, we may not know the value, but it's larger than 50 squared. That's the concept. However, if we were interested in, let's say instead of 51, we would be interested in 48 squared. Please understand, in this case, dx is 48 minus 50, which is negative. And the sign is important. All right. So what we need to do is to calculate f of x plus delta x. This is exact, and we are going to approximate it using this formula. So we want f of x plus delta x approximated by f of x plus dy. So that means we need f of x, which we already have it. We need to find dy. To find dy, we're going to go back here, differentiate f of x. So f prime of x, or dy dx is 2x. Dy is f prime dx. So dy is the product of these two, 2x dx. So we come back here, we replace the f of x with x squared, dy with 2x dx. Therefore, f of 51, this is 50 plus 1. F of 51, or 51 squared, can be approximated by this formula, where x is 50, same thing here, and dx is positive 1 because we are going up to 51. This is 2500 clearly. This is 2 times 50 times 1, 100. And the answer is 2600. Now, the actual value is 2601. And as you can see, they're extremely close because delta x or dx 1 compared to the choice of x is a lot smaller. So that's why they are extremely close. By the way, you may remember that you could do this in your head using a plus b quantity squared. I hope you remember that. You can say 50 plus 1 squared, which is 50 squared plus 2 times 50 times 1 plus 1 squared, and that gives you 2601. It can be done in your head, fairly simple. It's not a big deal. A plus b squared, I hope you remember. We can go with the linearization. That's another process which must give you exactly the same answer. So what it means is you don't have to memorize any of them. Just go with this. Find the equation of a tangent line at the function f of x equals x squared. What point? This point, not that point, this point. So we want to find L of x. So we're going to use this formula. What is the pair? 50, 50, plug in 2,500. What is M? So if you plug in 50 here, you get f of 50. That means 50, comma 2,500. If you plug it here, it gives you this slope. 2 times 50, 100. Now you know y minus y1. So I'm going to stick with just the good old point slope. Y minus y1, that means y minus 2,500 equals m, that means 100. X minus x of 1, x minus 50. This is 100x minus 5,000. Let me write it at top of it. So this is 100x minus 5, and then we have 1, 2, 3 zeros. We are going to move this and add it to the right, and we end up with this. And now I'm going to call it, instead of y, I'm going to call it L of x. This is the equation of a tangent line or linearization. What do we want? 51 squared, so we want L of 51. We want 48 squared, we want L of 48. So we're going to put 51. 100 times 51 minus 2,500, it's the same, and it must be the same. Otherwise, we have made a mistake, and I can't emphasize this enough, everybody. Questions? We want to use differentials to approximate square root of 27. Same concept. We are looking for a function to represent that. So all you have to do, just read it. Approximate what? Square root of 27. So what is the action you're taking? You let f of x be that action, square root of x. Now you want to choose a number. You want to choose a number x close to 27, for which the square root is easy to compute. Can anybody think of the closest number to 27 that we can easily do this? Anybody? Let x be what number? What is the closest number to?
25.
Say it again, please.
25.
Perfect. 25, because everybody knows the square root of 25 is 5. So if you choose x to be 25, what is your delta x? You're going to go from 25 to 27, so it's positive 2. 27 minus 25, because we're going to work on this class. Again, as an example, if we were interested in square root of 24, then 24 minus 25 equals minus 1. This would be dx or delta x. Be careful with that. So what do we need to do now that we have the choice of x? Delta x or dx has been calculated. We are going to go with delta y. This is exact. This is the approximation we are going to work with, which means I want f of x, I already have it. I want dy, I don't have it. I'm going to find it. To find that, that means I'm going to go with f prime of x and differentiate this. So I'm going to change this to x to the power 1/2. And then I'm going to say f prime is 1/2 x to the power of negative 1/2 or 1/2 square root of x. Then I'm going to say dy is the same thing times dx. So I tag along dx. Now I'm ready to work with this. I'm going to replace the f of x with square root of x. I'm going to replace the dy with 1/2 square root of x dx. I want square root of 27. That means I want f of 27. That means I want f of 25 plus 2. Meaning, replace the x with 25, dx with 2. Square root of 25 is 5. And we get 5 plus 1/5 or 5 and 1/5 or 5.2. And we are done. Now, if you use a calculator class, you get this. Of course, you really have to put a lot of decimals always. 5.196152423. However, if I'm just interested in one decimal, 1 changes to 2 because of 9, they become identical. So that's how close they are. Because 2 compared to 25 is fairly small. Here's the second method, linearization. Linearization. So I'm going to use the point slope formula, everybody, which means I need two things. I need a pair and I need the slope. What is my pair? Plug in 25 here, you get 5. So if I plug in 25, the pair is 25 comma 5. Here's f prime of x. If I plug in here, that gives me the slope. So in here, I get 25 comma 5. In here, I get 1 over, this is 25, comes out as 5, 1 over 10. 1 over 10. And now I'm back in business. I'm going to use the point slope. Y minus y1, which is 5, equals m 1 over 10 x minus x sub 1, which is 25. So on the right side, everybody, I have 1 over 10 times x minus 25 over 10 25 over 10 or 5 halves. I'm going to add the 5 with 5 halves, negative 5 halves with me. So negative 5 halves and positive 5 gives us positive 5 halves. This is the linearization. This is the equation of a tangent line. And I now want L of number 27. L of 27. And if you plug in and you work it out, this is 27 over 10 plus 5 halves, and it works out to be 5.2. I'll leave it for you to verify that. And this number is identical. Linearization should be identical to using differentials. Last question. Anybody wants to read this one for us?
Can you hear me?
Go ahead, please.
Okay. Measurement error. In a manufacturing process, ball bearing must be made with a radius of zero point 0.6 millimeters with a maximum error of plus or minus 0.015 millimeters. Use differentials to estimate the maximum error in the volume of the ball bearing.
Excellent. So let's see what's going on here, class. So what is given here? Here's the ball bearing. Okay. See, those are in the shape of a sphere. So spherical shape. And we should know the volume is 4/3 pi r cubed. Because it's talking about the volume here versus the radius. So we should know that. So what happens is that if this is the size we need, that means we need the radius to be 0.6 millimeters exactly. This is what we need to have, everybody. However, it may be larger by 0.015 millimeters, or it may be smaller by the same amount. So this is the size we need, r equals 0.6. It may be smaller. By how much? 0.015 millimeters. Or it may be larger by the same amount. So it's 0.6 minus 0.015 for the green one, or 0.6 plus 0.15 for the blue one. So this is your delta R or dr. This is your R, and the formula for the volume, we've seen it quite a few times by now, and we should know that. Let's see what we are interested in. So the volume is 4/3 pi r cubed. We are interested in finding dV. We are interested in finding dV. So therefore, let's differentiate, everybody. First, we are going to find dV dr or V prime of R. To do that, this is just a number, we keep it. So dV dr or V prime of R. This is a number. Now R cubed, as you know, becomes 3R squared. Number 3 and number 3 cancel each other, we get 4 pi R squared. This is dV dr. What is dV? Just like dy, which is f prime of x times dx, dv is dr times 4 pi r squared. So 4 pi r squared dr. Replace the r with 0.6 and dr with plus minus 0.015. We're going to square this number. We get 0.36 times 4 pi times 0.015, and we put a plus minus 5. And plus minus, and we get plus minus 0.0216 pi. And if you change the pi using a calculator, again, it's not 3.14, it's 3.14159, and it continues indefinitely with a lot of decimals. This is what we get, everybody. So plus minus 0.0678584 cubic millimeters. Now, we are done with the question. However, What if we wanted the exact? Remember, the exact is delta y. So in this case, delta v, the change in the volume exactly. So there are two calculations you have to do. One of them is to uh, calculate the area of the smaller one and subtract it from the volume when it's 0.6. The other one is that calculate the volume of the larger one and then subtract the volume when it's 0.6 from it. In other words, the following. 4/3 pi r cubed. If you go with the bigger one, in other words, 0.6 plus 0.15, this bigger one has this radius of 0.615 cubed minus the original one, 0.6 cubed, and you can calculate this using a calculator. Or for the smaller one, the green one, the one inside, then 4/3 pi 0.6 cubed minus 0.6 minus 0.015 becomes 0.585 cubed. If you calculate these two, it gives you the two limits, the smaller value versus the larger value. The difference is this is exact, everybody. This is an exact value, if anybody is interested.